are. Now I have to behave. I need an open hour from our meetings. Well, Perry, get back here.
Yeah, it's an all-encompassing life. I spent a few, first 10 years on the road too, so that's all about. So now they grow up, you get to see them.
So now we're moving on to chapter 4, which is inductors and capacitors. And as we go through this, you'll start to see a lot of the terms are going to start to sound familiar. This is where things start to build on each other, and you'll have a few, I've heard that before, moments. They say you'll get a charge out of this. I've seen better ones, but. So early on in chapter 1, Ron was talking about as you pass current through any conductor, it creates a magnetic field around it. The stronger the current, the stronger the magnetic field. And he also talked about the left-hand rule, where if you're holding an imaginary wire and your thumb is pointing in the direction that the electrons are flowing, your fingers curling over are the direction that the magnetic field is. So it's building in a donut, we just finished, donut-shaped field all around that wire. And in just a single wire, that force is pretty small. So what they do when they want to get some sort of useful effect out of it is they'll take several pieces of wire and wrap them one on top of each other, and with each turn, the field from one conductor builds onto the field from the next conductors, and they all add up together. So you can build some very strong fields. He was talking about an electromagnet at the metal shop where they pick up the steel. And that's just a big lump of iron with probably hundreds and hundreds of lines of wire inside there that gets electrified. And when you do wrap it like that, just wrap it around a rod, they call it a solenoid coil. And I have a few examples of it here. This is actually a special purpose one. It's the antenna out of an AM radio. Although it's a coil on a form, it performs the function of an antenna, which is not what we'll be talking about. And I also brought along a relay, also known as a solenoid, and that's where they get the term from. And if we see inside here, there's looks like a spool of thread with a bunch of wire on it, and through the center of that is a metal bar, and on the far end is a movable plate with some connectors on it. And when we energize the coil, it magnetizes the core, it pulls the plate in, and the connectors move. So it forms a switch that's turned on and off with an electric current. So the term inductor comes from the effect. As the current flows through a wire, that field that's generated is, they refer to that as the field being induced in it. So that's where the term inductor comes. Now, one thing that happens, and we'll get into this a little bit further, is, as I said, the stronger the field is, the stronger the current is, the stronger the field is, but it takes time for that field to build up. So initially, through an inductor, when we apply a voltage, there's gotta get it straight here. Initially, there's quite a low current until the field builds up, and then the current ramps up as the field builds up. And once it reaches its steady state, the field doesn't change, the current doesn't change. But if we suddenly take that current away, the field begins to disappear, and and it actually will create an electric force inside that wire that tries to maintain that field. And when we get into what happens with alternating current, that'll make more sense why that's a useful property. So there's different ways we can build coils. I showed, should go back, didn't mention coil. Coil is another term for an inductor, just because it's a coil of wire. So a lot of us don't call them inductors, we use the slang term coil. So I hope I don't slip up too much. I've got a couple of other ones here that are quite small. They're out of, I think, a radio. And the first one is a couple of little turns of wire, and inside the center you'll see a piece of black material, which is ferrite, which is powdered iron, mixed with some sort of binder to keep it together. And the second one is the same thing with a lot more turns. And what happens is, depending on what that core is, will change the properties of the inductor. Some materials like that bar in the antenna is greatly enhance the magnetic field. Other ones where it's just air, like this bad boy, is, yeah, it's very cold too. That one has a much lower inductance because the field inside it is air.
What exactly is that?
That would be out of an antenna tuner probably. That's 2 or 3 coils fashioned together. We like it because it's big and silver and shiny.
We're just trout here, we just like the shiny thing.
And the term that they use for the different properties of coils, or the cores, pardon me, is permeability. And you may see that term turn up on an exam as well. So an inductor, once the field is built, it will try and oppose any change to that, so we stored some energy in that field. And that's, so they're essentially storing a magnetic field is what an inductor does. And it will try to oppose any change. And I really like their analogy here of a flywheel. I'm not sure if anybody remember the old style tops, where you push a handle down in the center and it would spin the top, and the faster you pushed it down, the faster it would spin. That's basically what we're seeing in magnetic field around inductors. Difference is, when we pull the handle out of the top, there's a mechanism that lets us do that. If it didn't, the top would keep spinning and try to pull the handle out of our hand, and that's what's happening with an inductor too. So when we apply a current, the magnetic field builds. When we stop, it tries to keep that current flowing. And they talk about a few different styles in the book here, and why they might be won in different ways. There's one term here that I can't help saying that I've never heard in my life before, which is pies, where they have several coils put onto one form, but and I can't imagine there would be a question on pies, but they do have it highlighted. One term you will run into are the last two on page 4.3. When we have our inductor with the current flowing through it, and we take the battery off, the force that it creates is an electric force, which can be also referred to as an electromotive force, or EMF, and they refer to it as either back EMF or counter EMF, so a voltage opposing the change. And that you will almost certainly see in some questions. And they mentioned that the reverse voltage can be surprisingly high. In the good olden days, when we had coils.
Easy there, easy.
I had a car like that too. When our ignitions had a coil and a set of points in there, what happened is there's really quite a large inductor inside the coil in the older cars, and when the points broke, it created a back EMF, and that back EMF was tens of thousands of volts, which was enough to fire your spark plug. And so with a big enough inductor and the right amount of current, it can be surprisingly high.
Actually, the ballast out of a small fluorescent desk lamp will do a pretty good job too.
Well,
Yep.
good to know. Actually, I'll digress a bit. My wife's uncle always loved to do a great demonstration of that. He had a coil out of a Model T, and he did demonstrations for school kids, and he'd have the whole class stand around in a circle to hold hands. And he was at one end, and his wife was at the other end, trying to hold a straight face. And he let this thing go and watched the faces around there just explode as everyone got a little jolt. So AC in inductors. Oh, pardon me, skipped ahead. The term, or the unit for inductors is a Henry, abbreviated just to capital H. A Henry is a pretty big quantity for what we would normally run into. So this is, in inductors and capacitors, is when you're going to get into the fractional units. So although the unit is a Henry, quite often will be in millihenries, the small m in front of the H, or a microhenry with a little character called mu, looks like a little u, but so that's a millionth of a Henry. So quite often we'll be dealing in millihenries and microhenries when we're talking about circuitry. So inductors and circuits, when we're dealing with AC. Alternating current is what it sounds like, and Ron spoke about this earlier, where the current flows in one direction, then it flows in the other, back and forth. In this case of our power, 60 times a second. If we have that happening in an inductor, the inductor is going to try and oppose that change. So we can use those properties in certain ways, take advantage of those properties, the way it opposes those current changes. And we get into the symbols. This one is usually easier to remember. An inductor is a coil of wire. The symbol looks like a coil of wire. Some actually draw it with the little loops. Although I'm not very good at it. So that's a simple inductor, coil of wire like the big silver one. If we have a core in there, sometimes that's designated on the schematic symbol too.
Looks a lot like resistor.
It does. Very similar. And you can use that to your advantage later for remembering things. So this, without it, just says that it's a coil of wire with nothing in particular around it. With two lines here, means that it's a solid core of some sort, usually iron or something like iron. Yep. And if it's just wound around an open form with nothing in the middle, it's an air core, and it's usually a dashed line. And we actually don't have a variable inductor here, but if you picture that big one, some of them have a lot like the potentiometer, a wiper that will travel around and contact different points on the coil to make it variable.
This one does. This is switch.
Yeah, that one's switches different things in. And for variable, we do that. We put an arrow through the symbol. You'll see that for a couple of other symbols as well. And what that one does have is more than one connection on it. And those are called taps, and they're used to, well, they're used in different circuits in different ways. There's lots of ways you can use them, but essentially it's a connection in partway through the coil. And we will get into how they're used in other ways. And I mentioned that the behavior of the coil can be changed by the type of core. And the two little guys who are passing around, that core in there actually is threaded. It's like a bolt. So to adjust the coil value, we thread that core in and out. And there are some crystal radio sets that use that for tuning. They just move something in and out. Yeah, you can set that anywhere. Now we'll get into inductors in series and parallel. And this is where it comes to your advantage that this looks a lot like a resistor. The formulas for inductors in series and parallel are exactly the same as the formulas for resistors in series and parallel. So when they're in series, their values add together, and when they're in parallel, their values combine together to make the value smaller. So they do go through a bunch of different formulas here. I think we probably belabored that one enough for tonight. So when you're working with calculating resistors, just keep it in your mind you can do exactly the same thing for inductors. But the one thing to watch out for is those leading terms. Because they tend to be not in full henries, you have to be very careful, especially on the exam, to make sure those terms are correct.
So all the calculations are in henries?
All the calculations for everything are in what they refer to as the base unit.
Okay.
So volts, amps, watts, henries, farads for capacitors, ohms, and I can go on. I'm just going to put this guy up here. Micro. The symbol for micro is mu, so it's 1/1,000,000th, and you'll see it as written as micro something. And milli is a small m. So, transformers. Mentioned that current goes through, creates the field builds on itself. What happens if something else is near it? It's also going to be affected by that field, and we can take advantage of that as well. And that's one special case of a coil or inductor. You'll have a coil of wire on one side in one area. See if I have one here. I do. And on that same form, they'll have another coil of wire. And what happens is the voltage, or the ratio of the turns between the two sides determines the ratio of the voltages that we see on the inductor. So this one's actually used for a different purpose, but and that's they call it a toroid. It's a special kind of coil, and there's two windings on there, and each one works along with the other to be part of a complete circuit. And there's a couple of reasons for doing that. Some for safety, some for practical reasons. We've got 120 volts RMS coming out of our wall sockets, Not a lot of things can be powered by that. So we'll use an inductor, or two inductors together to form a transformer. If we put two coils near each other, there'll be some effect. If the first one has a core, we're going to have a field building around that core. But if that core is also shared by another one, we'll actually get magnetic field lines inside this core. So the magnetic field, if we're coming from the wall, the 120 volts creates here will create a voltage coming out the other side. And that's the little, I usually refer to as a wall wart. The older style plug-in AC adapters is what most people refer to them as. And the way to figure this out is perhaps the simplest formula you'll ever learn. The ratio of the turns, exactly. The number of turns here compared to the number of turns here. So for our wall transformer, we want 6 volts coming out to power something. For every 20 turns on the 120 volt side, we'll have 1 turn on our 6 volt side. So we'll have 120 volts, alternating current coming in, 6 volts, alternating current coming out. Now I'll do some other things to it to turn it into something useful. If you look up on the power poles, that's exactly what you're seeing there. The transformers that take 14,000 volts off the high voltage line and turn it into 220 volts to come into your house. And all that's inside those big cans is a bunch of wire and some oil and so on to keep things cool. And depending on this ratio, they're referred to as step up or step down. So this one is a step down, it's going from 120 to 6. If we did something like the inverter you have to give you 120 volts in your car has something similar, steps it up. So it would feed in here and feed out the other side. And there is something called a one-to-one transformer, and that's used for something different than this. We've got one circuit over here doing something, another circuit over here. They're getting their power from different places, they're doing different things. We don't want them electrically connected to each other, but we want signals to go back and forth. So we'll have a transformer that hooks them together so it gets the signals from one to the other without having any electrical connection between the two. And that little transformer I sent around is the special one. We've got another one here. This is your classic style transformer. It's built out of probably about 50 layers of steel sandwiched together. And then the coil of wire wraps around the middle of it. And the problem with that is what they call eddy currents. Yeah, we've got magnetic fields going through here, but magnetic fields don't like corners. They don't like discontinuities and things, so it's not as efficient. And so a transformer like this will create more heat for the amount of work than other ones will. And that's where our little donut one comes in. It's called a toroid or torus. And because it's a nice round circle, it's much more efficient at keeping the magnetic field lines inside the core and making useful value of it instead of creating heat and interfering with things outside. And I should really speed up a bit. So the transformer that keeps two circuits apart, that's just referred to as an isolation transformer. And there is something called, on page 410, called hysteresis. And in general terms, hysteresis is when something happens, when something changes, it also changes what it takes to flip it back. So you can think of the older style light switches with a good snap to them. You give it a good push until it gets to the middle, then it snaps over. Now to get it back, you have to give it a good push until it gets to the middle and it snaps over. That's hysteresis, as opposed to something that is exactly the same all the way through. So, and the effect there is it changes the properties from the ideal calculations that you might use. Now, capacitors. Capacitors, or if you read any British magazines, they'll be called condensers. And just as inductors store magnetic fields, capacitors store electric fields. And they are incredibly simple. They're nothing more than two plates separated by an insulator of some sort. And strangely enough, the symbol for it is that. Two lines with wires coming out the side with nothing in the middle. And we have some examples of capacitors. Where's the big one? That one's out of a power supply.
In power supply.
By today's standards, it's not that big. And what's inside there is a sheet of aluminum with an insulator on it, another sheet of aluminum, all wound up into a coil or a little jelly roll with some fluid in there to enhance the properties. This one is a big variable capacitor, and if you look through it, you can see there's plates and there's nothing in between them but air. And by rotating it, we'll change the value, and we'll tell you how in a second. And we have his little brother out of an AM/FM radio, an old style one. There's actually 1, 2, 3, 4, 5 capacitors plus another one up here. 6 all working together. Exactly the same concept, only just much smaller. So what happens here? When we hook a battery to a capacitor, initially there's a high current flow. And what happens is our electrons deposit on one side, and they build up there. So that you end up with a big charge, electrostatic charge they call it in between. And if we were to take this away, or open the switch, that will hold its charge for us. In some cases for very long times, for some cases it's very small values and very, very short times, but it does hold a charge. And I skipped ahead one thing. This insulator in here has an official name, it's called dielectric. So you might see that on the exam. So the dielectric is the insulating material. And just like inductors, the material that's used changes the properties. So air or the insulator in that big wound up one, they'll have different values. And I just want to make sure I don't, nope, we're going on to that next. And on page 412, they just show you a few different styles of capacitors. I don't recall what this is. Anything that looks like a can or a chiclet is a capacitor. So they come in different shapes, sizes, and colors for different, made of different materials for different purposes. Now I'm not sure that you'll ever run into this on the exam, but on 412, they talk about the two parts of a variable capacitor called the stator and rotor. Stator is stationary, doesn't go anywhere. The rotator rotates and moves. Beyond that, I don't think you'll ever need to know it. at least in the context of the exam. And at the bottom of 412, there's a very special type of capacitor, which we'll get into more when we get into active circuits, and it's called a voltage variable capacitor. And by applying a voltage to it, we can change the properties of it. And we will get into that later, why and what that's used for. And on the top of that little one, I said there was one more little capacitor. They call it a trimmer capacitor, which is usually just refers to a small value capacitor that's used for making small adjustments, for trimming up a circuit. And the big one is referred to as an electrolytic capacitor. And they have one very important property, and that is that they're polarized. You have to have the positive and negative hooked up the right way. If you don't, they will explode.
Good times.
I know this from experience. Let's just leave it at that.
You had to test that theory out there.
By accident. A story for another day. So the factors affecting the capacitance, or the value of the capacitor. And that's one, the biggest one is the effective area of the plates, or how much plate surface area is in common with the other plate. And with the big variable one, you can see that quite obviously. You pass more and more of the other plate into the first set, and you get more capacitance. So in our case, if we make our capacitor a lot bigger, we'll have more capacitance. The separation between the two. Also, the closer they are, the higher the capacitance is. Up to the point where they touch, when they become a fire. And that's an important thing. There's a reason that big capacitor is so big and the little one is much smaller. The big one is made to withstand much, much higher voltages, probably in the thousands of volts before it'll actually jump across as a spark, and usually damage the process. So for something that needs to handle very high voltages, the plates are going to be far apart, but you need more of them and bigger to get the same value. For something that's small, you can squash them in tight, but you can't put as much voltage on it before it breaks down, is the term. And the other thing that changes the value is the dielectric material. So air, some use mica in here, some use ceramics, there's several different properties or different materials. And they just give you some examples here on figure 420. You won't actually have to know these values, but they're just used for example. And the dielectric material has a value, and it's referred to as dielectric constant, or K. And I don't think you'll have to use any calculations for that, but the term what is dielectric constant might come up. Capacitors in series and parallel. If you know how to do it for resistors and you know how to do it for inductors, turn it upside down and it's capacitors. So capacitors added together, or in series, the value will be smaller. So one of the things that changes the value of a capacitor is the distance of the plates. So if we have two capacitors in series, effectively, we've got one capacitor with the plates a lot further apart. And similarly, if we have two capacitors in parallel, we, in our heads, move these closer together. It's like having plates that are much larger. So their values add together. So the formulas, and working with the formulas, are the same concept as resistors and inductors, except you do the opposite one. In series, they work together to make a smaller value. In parallel, they work together to make a higher value. And I did mention once that some of the reasons for the different materials is to give them different properties. Another reason is to make them withstand different voltages. And every capacitor made will have a maximum working voltage. This is not the maximum voltage it'll tolerate. It's just the maximum it should ever be used at for reliable use. They'll usually go somewhat higher than that, but when they do, bad things happen. They either spark, they burn up, the little ones can actually pop. So the working voltage, or voltage rating they call it, or maximum voltage, are all terms that you'll see. And on the big blue one, it's actually got 40 VDC, 40 volts DC, stamped right on the side of it. So, then we get into reactance. And this is where things get really interesting. So an inductor tries to oppose changes in current. Capacitor tries to oppose changes in voltage. And when we put them together, they can work together or to oppose each other, and we can take advantage of both. So when we do have, as I mentioned with AC, if you try to pass alternating current through an inductor, it'll flow one way and it'll try and stop it flowing the other way, and back and forth. With a capacitor, it'll charge up one side, and then it'll charge up the other side quite happily. So it will act as if it's conducting an alternating current. So inductors block out try to block an alternating current, while capacitors try to conduct it. And you will have to work with the formulas on page 416 and 417. And even though pi is in the formula, typically the answers are simple enough on the exam that just using 3 or 3.14 in this case will get you close enough to know which answer is right. If you're really calculating things for building a circuit, of course you want to use the real values. So reactance is, symbol is X. And I like to think of it as, or tell people to think of it as all our AC resistance. Resistance for alternating current. Where resistors are the same for both, but we learned about them for DC. And the reason I tell people that is because the term is still ohms. So reactance in an inductor and a capacitor are, the term is ohms as well. And the equation for a capacitor is, oh, sorry, wrong one, inductor. I don't want to get it wrong. Quite often they'll say XL. L is an inductor. So the reactance of an inductor is 2 times pi times the frequency, how fast the alternating current is changing, times the inductance. And the frequency will be in hertz, cycles per second. The inductance will be in henries. And the resulting value will be expressed in ohms. And for capacitors, it's a very similar formula. Again, their inductors equal twin.
Look at that again.
Thank you. So it is 1 divided by 2 times pi times the frequency of our alternating current times the capacitance in farads. That's what I didn't mention. The term for capacitance is a farad, capital F. And when I was taking my electronics many years ago, they said you'll never see a 1 farad capacitor. Every obnoxiously loud stereo you hear driving down the street has a multi-farad capacitor in the trunk, keeping the headlights running. That's the idiot.
That's the idiot
But for all practical purposes, we're usually dealing in microfarads. You won't see a millifarad. I've never seen it done that way. Nanofarad, which is 1/1000th of a microfarad. And that you typically will only see in European publications. It doesn't get used here much. And picofarad, lowercase p, which is 1/1,000,000 of 1/1,000,000th of a farad. The big blue one that went around is a 40,000 microfarad. So to get even into the thousands of microfarads, things are getting kind of big. And some of the little dots you saw on there were picofarad value of capacitors. So, what can we do with these two that like to fight against each other? Well, we can put them together. When we do have both inductance and capacitance in a circuit, they both work together to give us a final value, which is called impedance. And it's similar to a resistance, so it's also expressed in ohms. This is where things can get a little confusing. It's a different value, but it comes out in ohms again. And on page 418, they quite often there will be resistors in part of it too. They show you a formula for calculating the impedance of a circuit with both resistance and reactance, X. I don't know if you ever will see that on a test though. And I'm actually not going to talk much about impedance matching. We'll get more into that in antennas and feed lines. But what I really wanted to cover is resonance. And that's really where inductors and capacitors work together to give us something really, really neat. And I always have to look at my sheet here because I don't want to get it backwards. So we have an inductor and a capacitor together in a circuit. They'll work together. For an inductor, as the frequency goes up, the more it opposes it. For a capacitor, as the frequency goes up, the more it passes. And there will be a point where those two match, and that's called resonance. Where the inductance in a circuit and the capacitance in a circuit both come out to the same value, and that's referred to as resonance. And where it gets interesting is when we have them in series and parallel. Oh, sorry, forgot to put my capacitor in there. And what happens is when it's in series, if our frequency is very high, the inductor is going to block it. It's not going to let very much of it through. If our frequency is very low, or DC, the capacitor is going to block it. But there is a point, as we go in frequency here, from low frequency and high frequency, when we hit resonance, both will work together, and it will pass the signal through. And where we take advantage of that is the older style of radios with our tuning capacitor, worked with an inductor to tune in the station you want, rejected all the others, and it only let through the one you wanted. And the other one is a little bit harder to visualize in your head. But it, at very low frequencies, it's going to pass through the inductor. At very high frequencies, it's going to pass through the capacitor. But when we hit resonance, it'll block them both. Or it'll block the most, I should say. And we use this, it's called a blocking filter, a notch filter, all sorts of things. My outside ham radio, I can't think of a good analogy of where you'd use it, or where you would see it in everyday life. But what it's used for is to get rid of a certain signal, or stop a certain signal from coming through. And when we get into antennas, we'll show you how we use one of those to our advantage. And we talked about with capacitors and inductors, the material that's in the middle changes their properties. And when we put the two together, the properties of those insulators or cores work together to form a quality factor, or Q. And this actually, they refer to it as a, what's the term? Unitless number.
Yeah.
It's just a number. It doesn't, it's not ohms, it's not volts, it's nothing. But what you remember is the higher the Q, the higher the quality. The higher the quality, the sharper this transition is. So when we have a special kind of filter that we use on our radio repeaters like we were talking through tonight, where they're built to selectively stop very, very small portions of the signal while passing almost everything else. And in some cases, they will put several of these together. It's the higher the quality of the Q factor, the more difficult they are to make. The more difficult they are to make, the more expensive they are. Sometimes they'll put 2 or 3 in connected together to enhance each other. And the quality or Q value will be on the test. Guaranteed that. And either one of these, you'll actually need to know which one passes and which one stops for the test. And they're both referred to as tuned circuits. A circuit that behaves in a particular way at only one frequency. Or is supposed to only behave one way, only one frequency. So we got a little more into formulas. Again, not a huge departure from what we saw in resistors, but when we start calculating resonance and impedance and so on, the formulas get a little more complicated. You start getting into squares and square roots. So yeah, you will, although there won't be much of that on the exam, having a calculator handy will definitely be a good thing. So, do you have any questions about anything tonight, actually? Wow. Silence is deafening.
We've baffled them with,
We've either done something very good or very bad.
actually the question I'm looking for is why? The answer is because.
So for next week, we'll be getting into waves and wavelengths, where we start talking about what does this frequency mean and do, and the bands, and in particular how they relate to ham radio. We've got the different frequencies are broken up so that we refer to it as different bands. And we also get into propagation. Once you get your signal going somewhere, how does it get there, and so on. Don't let chapter 5 scare you too badly. The last 6 or 8 pages are tables, which you're not going to have to memorize. okay? Just so you're not,
You want sort of a general picture of them, but you don't need
Yeah.
the details.
exactly. And whereas with propagation, there's quite a bit of memorization there. The terms, the different layers we talk about and so on. So as you're skimming over these two chapters, in chapter 5, don't worry as much about the details, and chapter 6, a little bit more on the nitty-gritty details. But that's it for tonight. And we'll see everybody next week again. And don't forget to work out the regulations.